Hello, welcome to this presentation of Topic 79. My name is Andrew Jensen. I am a master's student in computer science at Northeastern University, and I am enrolled in CS5330 pattern recognition and computer vision for the summer 2026 semester. This presentation was created for the purpose of Assessment 1, Classical Vision Topics, and it addresses my assigned topic, Topic 79, PCA, Concept of an Eigenspace, How to Project Something into an Eigenspace. This presentation is organized into 5 sections. Let's begin with the setup. Here is a bird's eye view of Assessment 1. Assessment 1 covers 95 topics. PCA is covered in topics 76 through 82. As stated in the assessment's instructions, I will assume this audience already has a background on topics 76 through 78. My topic, 79, addresses specifically the concept of an eigenspace and how to project something into an eigenspace. And the remaining PCA topics, topics 80 through 82, will be covered in separate presentations. This presentation uses the following sources. I used Professor Maxwell's lecture notes and 3 published papers, Turk and Pentland's 1991 paper on eigenfaces, Maras and Nayer's 1995 paper on visual learning and recognition of 3D objects, and Key and Saktharkar's 2004 paper on PCA SIFT. Here is the math notation used throughout this presentation. D is denoted as the dataset, N is denoted as the number of vectors, M is denoted as the number of features, X sub I is denoted as the ith sample, mu sub D is denoted as the mean vector of the dataset, X hat sub I is denoted as the centered sample, E sub J is denoted as the jth basis vector, K is denoted as the number of selected basis vectors, G sub I is denoted as the coordinates of X sub I in the k-dimensional eigenspace. The next section addresses the central question, what is an eigenspace? An eigenspace is a reduced k-dimensional coordinate space down from the original m-dimensional feature space whose axes are the top k eigenvectors, principal components, ranked by eigenvalue magnitude, largest to smallest, and labeled E sub 1 through E sub k. Let's look at a simple example. Starting on the left, we have the original data of data points scattered in 3D space. But you'll notice that they lie close to a flat 2D plane tilted through that space. That plane's 2 axes correspond to the top 2 eigenvectors, which is displayed in the graph on the right. As you can see, describing each point using only its position along those 2 axes preserves nearly all of the original information while reducing dimensionality from 3 to 2. This reduced representation is the eigenspace. Next, I will describe the procedure for projecting a data point into an eigenspace. Assume the training set and the top k eigenvectors have already been computed using methods covered in topics 76 through 78. For each training vector, x sub I, after preprocessing, there are 2 steps. Step 1. Center the sample by subtracting the dataset mean. This gives you x hat sub I. Step 2. Project the centered vector into the eigenspace by computing its dot product with each of the top k eigenvectors, E sub j. This produces G sub I, the vector formed by projecting x hat sub I onto E sub 1 through E sub k. The result is that every training sample x sub I now has a corresponding coordinate g sub I in the eigenspace. Next, this procedure is useful because once an eigenspace has been calculated from a training set, any new unseen input can be mapped into that same space to obtain its low-dimensional coordinates. The steps are identical to those used for the training data. Ensure that the new unseen input has been preprocessed, similar to the training data. Then, follow step 1. Center the new input x sub new using the same mean mu sub d that was computed during training to get x hat sub new. Step 2. Project the centered input using the same top k eigenvectors used for the training. The result is the new input vector x sub new now has a corresponding vector g sub I sub new in the same eigenspace as the training data. It is important to note that the mean and eigenvectors from training are reused, not recomputed for the new sample. This is what allows a new input to be compared to the training set within the same coordinate system. I will now present a few applications of eigenspaces drawn from the research papers. This table quantifies how much smaller the eigenspace is relative to the original data across all three cited papers. Turk and Pentland began with 65,536 dimensional images, and they reduced that to as few as 7 or as many as 40 dimensions. Maras and Nair reduced 16,384 dimensions down to 20 dimensions. And Key and Suk Thakar reduced image patches of just over 3,000 dimensions down to 36 dimensions in order to achieve their best matching performance, and was able to obtain good results by reducing down to 20 dimensions. For image correlation, Maras and Nair's 1995 paper explains that in image compression and pattern recognition tasks, eigenspace is optimal for computing correlation between images. The closer the projections are in eigenspace, the more highly correlated are the images. As a result, comparing images can be performed using their eigenspace coordinates rather than their raw pixel values, which is significantly less computationally expensive while still capturing meaningful similarity. With respect to time and space, in Key and Sukthakar's 2004 paper, they explained that for image retrieval applications, compared to the standard SIFT algorithm, which uses smoothed, weighted histograms of the image gradient, the author's PCA SIFT algorithm applies PCA to the normalized gradient patch, projecting it into a 20-dimensional eigenspace. This results in less storage and faster matching. So now I've finished covering topic 79. Next, I will summarize the key points of this presentation. An eigenspace is a reduced k-dimensional coordinate space down from the original m-dimensional feature space, whose axes are the top k eigenvectors, principal components, ranked by eigenvalue magnitude, largest to smallest, and labeled E sub 1 through E sub k. And here is the formula for how to project something into an eigenspace, where G sub I equals the coordinates of X sub I in the k-dimensional eigenspace. Lastly, here is another simple 3D to 2D visual example, with the left side showing the original data set and the right side showing the data after being projected onto the eigenspace. Thank you for your attention. If you have any questions, feel free to connect with me via email. This concludes my presentation on topic 79.